warm month this year. This is 2015 when it was here. That was a pretty warm March. All right, well, what does this mean? Pun almost always intended. I do usually mean the puns. Accidental puns are when they just happen and you're not thinking about it. What does this mean? What is it telling you? Does it mean that March 2015 was always warmer? Consistently warmer? Typically warmer? Those are, well, always is a pretty clear term, like every day, which if you think critically, think logically, that sounds like it probably is not true. It probably wasn't warmer every day. Temperatures go up and down, there's variation. Was it consistently warmer, like most days, or maybe over a 3-week span, was it always warmer except for maybe 1 or 2 days? Typically, what does that even mean, typically? More than 50% of the time? I suppose you could say that's a definition of typical in the situation, more than half the time. It's unclear, actually. It could mean always warmer, could mean consistently warmer, could mean typically warmer, more than half the time. It was warmer in 2015 than in 2014. But it might not mean that, actually. It could be the days in 2015 and 2014 were most of the time almost exactly the same, but one day in 2015, it shot up to 100 degrees. It never happened. Not in March in Minneapolis. It could mean that, and that would pump the high, the mean, for 2015 up. Maybe not that significantly, but enough to see a difference. We don't know yet, without looking at the numbers themselves. Does it mean the high temperatures over the course of the month for each year were consistently near these values? Meaning, in 2014, during March, was the high typically in the low 30s to mid 30s? Was that way for 90% of the days? And in 2015, it was close to the mid 40s pretty much every day? Again, if you think common sense even, if you think common sense about it, it doesn't seem right. Not necessarily is probably the best answer for those questions. The answer could be yes, could be no. We wouldn't know without looking into it further. It must mean something, though. Got to get to that. What kind of information about the data are we missing only with these numerical summaries, these means? They're called statistics. Means are examples of statistics. Anybody have any idea? What kind of information might we be missing?
Each day, the temperature.
Yeah, what was the temperature each day? That's certainly one thing we're missing. And what, for March, when it's spring, transitioning from winter to summer, what do you think, what else do you think you would see in the data? By the way, if you say data, it's okay too. I say data. I watched a lot of Star Trek Next Generation 25 years ago. Data.
Like your honesty.
What's that?
So like your honesty.
Thanks.
High and low.
High and low?
Would it be helpful to get information from like February, January to see how the winter?
Maybe. But what if we only focused on March? What do you think you would see?
Maybe the snowfall.
That might be helpful. It might be colder on snowy days.
The temperatures at the beginning of the month compared to the temperatures at the end of the month.
Yeah, that's getting closer to what I'm after.
The range?
The range of values, yeah. I'm thinking about over the month. I'm trying to hint at a graph here.
Distribution and outliers?
We're going to get to that, but I'm thinking something simpler. I'm glad you're trying. What's my arm doing here? What do you think I'm doing? Maybe you just can't tell what I'm doing. Am I signaling clear? Thinking of a graph, maybe it goes up, down.
The change in temperature.
Slope is not negative, it's positive. There's an upward trend, right? slope is positive. Now, does that mean the data are going to be exactly on a straight line? No. Right? That should make intuitive sense too. But that's one big thing we're missing is trend over time. We need to make a plot, and that's what I did here. In the next slide. These are called time series plots. We're looking at the high temperature over the course of the month. And it's interesting, both years had a similar pattern. That doesn't always happen. But both 2014 started pretty low, went pretty high, went back down, and then high again. Though overall, there's a general upward trend from highs 10, 20, 30 or so to highs more like 50 to 60 or 40, 50, 60 or so. Very good. See that? It's not a straight line. It's an upward trend. Though more specifically for these years, there's a up, down, up. That doesn't always happen every year, but pretty much every year in March you can expect a general upward trend. It would be a very rare March that is very warm at the beginning of the month and very cold at the end. I suppose it could happen once in a long while, but that's pretty rare. Usually the slope of the trend is going to be positive for March. It's springtime, right? Springtime in Minnesota could be snow. It snows a lot in March, but then the snow melts faster, right? If you're not from Minnesota, anybody not from Minnesota? Anybody? A few people. Anybody from the South? You are? Okay. All right. January snow doesn't go away for a long time. Okay. It snows this November, December, January. Typically, the snow stays there. Actually, it might be going down a little bit. You just can't tell. But in March, the great thing is the snow comes and it goes within a few days. It melts faster. Actually, 2013, anybody remember the spring of 2013? We got a big snowstorm May 3rd. Yet, a week and a half later, it was my daughter's graduation party. It was like 80 and there was a thunderstorm. Okay? So, that's pretty rare to get snowstorm in May. Sometimes you get flurries, but it's pretty rare to get a snowstorm in May. But it can happen. Okay? So again, this is called a time plot, or a time series. You're graphing the high temperature as a function of time, the data points, and you're connecting with straight lines. You don't have to connect them with straight lines, but it does help you see the trend better. And typically people do. And it does show you that overall, 2015 in red was higher than 2014. And it was consistently higher. It happened, oh, I got this for this purpose. A 2-meter stick. Wow. Powerful. 2-meter stick. What was I about to say? I forgot. Oh yeah, it was consistently higher over, it looks like, what is that, about a 2-week time period, 3 weeks? From about March 5th through March, what is that, 22nd? I can't quite tell. Actually, these lines are not one-day lines. That's unfortunate. Okay, somewhere in that kind of range. March 4th, 5th through about March 21st, maybe, halfway between 18 and 24 over there. March 2015 was consistently higher. What typically happens in weather is, you have warming trends and cooling trends. Periods where it's warm for a while and then cool for a while. That's what typically happens with weather in Minnesota. It's not usually higher than normal one day, lower than normal the next day, higher the next day, lower than normal the next. So, I mean, sometimes that happens. It's not like it never happens, but that's not typical, I don't think. Here's another thing we're missing: a sense of spreads of the distributions. Here's what you said there, right? What are you? You're saying the spread, the distribution. Something called a stemplot that you can make to try to see how these quantities, these numbers, these high temperatures are distributed. Emphasis on the word distributed. are going to make a stem plot on the board here. These stem plots, the book calls them stem plots, they're also called stem and leaf plots, are going to show us the distributions here. I need to look at the numbers. Let's see. The data. I've got the data in a Google spreadsheet that's just called Sheets. Up until about 6 months ago, I always used Excel. Sorry, Microsoft. Now I'm on to Sheets because that's what most people use. Seems to do basically everything Excel can do. Sometimes you have to add on extra features to it. And it seems to work basically the same way as Excel. You can certainly use Excel if you like. And maybe I will sometimes too, but right now I'm using Sheets. And it's something that I can share with you. I haven't done that yet. So here we have the actual data, the raw data, sometimes people say. How do you zoom here? Why is this? Okay, here's a, maybe I better just do a control plus, huh? There's our zoom. Okay. I was thinking that was maybe a way Sheets was not as good. March 2014 highs in this column, March 2015 highs, and in Fahrenheit here you could convert them to Celsius. So these are the data values. Let's look at the March 2014 highs. Let me copy and paste those over to the right here, starting in row 1. I'm assuming people have seen spreadsheets before. See any yeses? You can say no if you haven't. Okay, you've got numbers in these cells. These rectangles are called cells. There they are. I copied and pasted them over there. And if before you make a stem plot, at least if it's a fairly big data set, and this is fairly big, it's 31, I wouldn't want to try to make a stem plot without ordering the numbers first, from least to greatest. I think that's probably under data, sort. I'm guessing A to Z is low to high. My guess could be wrong. There we go, low to high. See, the numbers are starting low and going higher. This is not in the order of the dates, 1st of March, 2nd of March. If you look back at the ordering over here, there we go. I don't know what happened there. My data got corrupted. I don't know what happened, and that's not right. I think it was 3 the first day. Somehow my data got corrupted. Oh, and it did an automatic save. I guess that's a downfall of Google Sheets. It did an automatic save. I don't remember what it was. I think it was 3. I'll have to look it up on Active.
Go back.
Can you go? Can you? Oh, like,
There's a back arrow on the top right by the print.
There we go. Okay. I don't know why it did that. Maybe there's deficiencies in Sheets that I don't know about. Just copying and pasting here. That's all I did. Okay, now again, data, sort, low to high. Oh, did it change the plot?
Yeah.
Oh man, what a little, I need to practice this more. On YouTube forever. The same thing. I don't know what's going on here. Okay. I'm not liking this. Maybe I better go back to Excel. Maybe I needed to paste specials.
Maybe this YouTube video can be a blooper.
Yeah, okay. You can highlight that there's bloopers available.
When you're trying to make a YouTube video faster.
That definitely could be good. That can happen a lot. Okay, so if you're going to make a stem plot by hand, it's good to have the data in order from least to greatest, like this. And that's what I did with the sorting. When you make a stem plot, you want to first draw a vertical line. You want to look at your data and you want to say, what's the nature of all the digits except the last digit? In this case, the digits before the last digit are the tens place, although the first 2 numbers, 3 and 8, you would think of the tens place as being 0. 0, 3, 0, 8, 10, 19, 22, 24, etc. So all the digits except the last digit are essentially 10 spots. Now these numbers could have been in the hundreds if it was really hot, or if we're not talking about temperatures. And so then you'd want, maybe if there were lots of numbers in the hundreds, and I'm talking hundreds, 200s, 300s, 400s, you'd want to focus on the fact that those numbers in front of the last digit include both the 100 spot and the 10 spot. In deciding what your stem should be, in this case, the 10 spot is going to be the stems. 0 for the 0, 3, and the 0, 8 for the 3 and the 8, really. 1, 2, 3, 4, 5 for 10s, 20s, 30s, 40s, 50s. Highest temperature was 60. And then you want to make leaves on the other side of this line corresponding to these stems, and the leaves come off the corresponding stems. And that comes from the last digit, though sometimes with the last digit you want to do some rounding first. I forgot to say that. Sometimes you want to round your numbers before deciding what the last digit is going to be. Okay, this is kind of an art in deciding what the stem should be. It takes practice, it takes examples. In this case, again, the stems are the 10 spot and the leaves are going to be the 1 spot. So going back up to the top, there's a 3 and an 8. Put those next to the 0. That represents two data values, a 3 and an 8. Because this is a 0 and that 0 is the 10 spot. In the 10s, there's a 10 and a 19. Put a 0 and a 9. It's important to line these digits up vertically. That's essential. Don't be lazy about that. And on a test, if I have you do a stem plot, if you're lazy about lining up the leaves vertically, you don't get full credit, because that's part of the point of these plots. And this is a plot, as we will see. Look at the next group in the 20s. 22, 24, 24. 24 occurs twice. 25, 26, 26. 26 occurs twice, and 29. Write those 1 spots down here and line them up vertically. There's 2 24s, so put 2 4s. And 5, 2 6s. You should also put approximately the same amount of space between digits, except if you're putting 1s, which don't take up much room. 6, 6, 9. In the 30s, we have 30, 31, 31. Notice how I'm lining up these 1s underneath the digit above. 33, 35, 36, 37, 38. Line up well enough. Not as well as could be, right about like that. That's a little bit better. Now I go to the 40s. 40, 43, 44, line them up vertically. 340, 444s. What's that? 240s, thanks. Don't make that kind of mistake. 444s and 145. In the 50s we have 50, 53, 58, and we have a 60. Again, the video you can go back and forth. You're good to see that? What's the point? The point is this is a graph showing the distribution of these data. In other words, data is always plural, or data is always plural. If you want singular, you say datum or datum with an M at the end. These data, don't say this data. Say these data. I suppose I may make the mistake and say this data once in a while. If I do, I meant these data. Okay? I won't take off points for spelling this versus these, but in reality, it's these. These data, how are they distributed? What you do is you take your head, you can do it with me if you like, turn it sideways, 90-degree angle. What do you see? I see a bunch of sideways numbers. You see a graph that's got a trend like that. Bell-shaped curve. Normal curve. You heard of that before? Yeah. The bell curve? We see it. Cool. That's why I get excited. I see the distribution and I see it centered in the 30s or 40s. The mean is a measure of central tendency. What was the mean for 2014? Well, this might not be right anymore. The mean was, what? 33.9 in the 30s. Yeah, I mean, my drawing's not perfect. I mean, these three columns have almost the same number of data points in them. So yeah, it makes sense that the mean would be in the 30s more than the 40s. Right there. You can see visually what the number means about this distribution. There's also spread in the distribution. There's variability. Got 8 more minutes. You gonna hang with me here? There's variation. They're not, every day wasn't 33. The numbers vary. That's measured by the spread. Now the simplest way to measure the spread is to say what's the high and what's the low. The high was 60, the low was 3. And again, this 0 represents 60 because it's a leaf by the 60 stem. This 3 represents a 53. It's a leaf by the 50 stem. Their spread, high to low, 3 to 60, is 57. The overall spread, which is also called the range, is 57. The range is very sensitive to outliers. If we had a 100-degree day, that would really make the range a lot bigger. It would be nice to have a measure of spread that is less sensitive to outliers. And the main measure we're going to use is called the standard deviation, though that is not completely resistant to outliers. It still is sensitive to them, but not as much as the range. Coming back to Stemplots, I did it for both 2014 and 2015. I thought I had a, okay, yeah, I have a website you can go to and make Stemplots nicely. I made it for both of them, and I purposely made them a little off from each other here. That's 2014, that's 2015. Notice I lined up the 10 spots. The lowest temperature in 2015 was a 12. The 2 in the one up to the right of the one stem represents 12. That was the lowest high in March of 2015. Match that stem up with this stem. That's why I put this one low. Match it to the 3s, the 4s, the 5s, the 6s, and there was a 70-degree day here in 2015. What do I see when I look at these distributions? I do see that definitely the 2015 was a little warmer. The middle is in the 30s for this one. It's in the 40s evidently for this one. As we saw, it was like, what, it was 44 point something. That's one thing I see. What about spread? The range over here was 60 minus 3, 57. The range over here is 70 minus 12, 58. There's about the same amount of spread as far as ranges go. How about amount of spread in terms of a more robust, less sensitive to outliers measure? Is the amount of spread about the same or pretty different? It's hard to say for sure, though I would say it seems about the same to me, actually. Sort of maybe focused on the main group of numbers, thinking about being close to the mean there in the 30s. Between 20s and 40s is kind of typical for a high temperature in March here in 2014. Being between 30 and 50 was pretty typical for a high in 2015, though there were more in the 60s than you might expect. So that's hinting to me that a more robust amount of spread, measure of spread, that's more resistant to outliers, might be pretty close for both of these. A pretty similar kind of measure of spread. Maybe with this one being a little bit bigger because of lots of 60-degree days. The standard way, pun intended, that we are going to measure spread is with this thing called the standard deviation. Now on Thursday we'll talk about something called the interquartile range as well. But mostly we're going to be using the standard deviation, which has a complicated formula. So we're just going to use the computer and the calculator to calculate it today. By the way, that's a website that'll make Stemplots for you. That's where I made those Stemplots. Our most common measure of spread is called the standard deviation, or more specifically, the sample standard deviation. I'm not going to show you a formula here right now. On a spreadsheet, whether it's Excel or Sheets, you use a function called equals stdev to find a standard deviation for a sample. Don't worry about what sample means right now. Equals stdev. I got parentheses to the right of that. There is stuff that should go inside the parentheses. Let me illustrate that right now. What goes inside the parentheses? On a spreadsheet, you take the numbers and you put their cell references, their addresses, like this one has a reference of C25 right there. You put those inside the argument of the equals stdev function. And you got to put an equal sign first, that's why I'm always saying equals. So for example, if I wanted to find the standard deviation of, say, a group of 5 numbers here, let's start with 44, I could highlight those numbers, 44 to 57. Or I could type what you see here, C24 colon C28. The underline comes automatically. It's actually telling you the answer right here. So you can also enter this 9.9348 approximately. That's how to do it on a spreadsheet. Doesn't tell you what it means. Let me show you how to do it on a calculator. A TI calculator, at least. Go to stat mode. When I go to my stat mode, it looks like that. If you have a fancier calculator than mine, yours will look fancier probably. In stat mode, we can edit, we can do calculations, and we can do what are called tests, which we'll get to in chapter 6. In edit mode, that means you plug the numbers in. You're editing the data. I don't remember what those numbers were. I already have some numbers in here. If I didn't have, I could plug them in. That's in this column, this one. It's kind of like a spreadsheet. And then I go back to the stat menu and go over to calculate. And the simplest one to use is one variable stats. And if you don't put the list name in there, the default is the first list 1. So I can just enter this. And the mean is this thing. It's called X bar. Those numbers are 20.333 approximately. It's probably 20.3 repeating, it looks like. And there's some other numbers. The standard deviation that we want is this S right there. S sub X. S, the standard deviation of the variable X. That's a standard deviation too with a sigma here, that funny looking thing. Ignore this one. It's called a population standard deviation. End class in about 30 seconds. Let me point out in the PowerPoint that I also have a formula for the mean. On a spreadsheet, it equals average, not equals mean. Here's a symbolic formula for the mean, the last form of which is the lazy form, which I will talk about more on Thursday. X bar is the symbol for the sample mean, and you always say it that way. You say X bar, it's got an X with a bar over it. And finally, this last page on the PowerPoint summarizes the main conceptual facts to know. Quiz, 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 quiz. Future quizzes could include conceptual facts like these. Okay? We're out of time if I can get you out early, so if you'd like to stay and write those down, it's fine. You can also just download it off of anywhere.